Hello guys, welcome you all for this session of AIML end-to-end session where we're going to learn everything in order to become a data scientist. Hope you guys are enjoying this session, a long series. So I think nearly like 20 plus days, I think so. So we are enjoying a lot. So please guys, please watch all the previous video as we are telling again so that you can have a better understanding of what we are telling now. Okay. So like in the previous session, we have just have an understanding of what is supervised learning. In that we have learned about classification and we have seen one model like logistic regression. So please guys, please watch the previous video before you are coming to this video so that you can have a understanding of what we are talking. Okay, so today we're going to continue the classification model and we're going to wrap up the classification model that is under the supervised learning. Okay, so directly jump into the session. So decision tree. Okay. So decision tree are a non-parametric models that partition data based on the features and create a tree-like structure to classify data points. They are initiate and easy to understand. Okay. The thing is, this decision tree do classification in a manner of tree-like structure. We have a root node and we will have a branch and we will have a leaf. That's it. Okay. So let's see what are the things that we have. A root node, the starting point of tree representing the entire data set. Okay. Internal nodes, nodes that split the data based on the feature values. Further, okay, from root node we will be splitting. Leaf node, terminal node representing the predicted class for the particular data points. That leaf node will have the final result. Okay, I will put it in the simple manner so that we can understand, right? We are having a basket. Consider the basket as a data set. We are having the apple and the banana. Okay. Now that is a root node. Now let us consider shape is a feature. Okay. We are having a like a circle and not circle. Okay. If it is a circle, it belongs to apple. If it is not a circle, it belongs to banana. That's it, right? Now we're gonna have one more class that is called as a color. Okay, if it is yellow, that is banana. If it is red, that is apple. Okay, so the topmost thing, the basket, is called as a root, and the middle part, that is the shape, circle not circle, that is called as an internal node. And the final thing we are having, right, size. Okay, sorry, color, we are having yellow and then red, that is what leaf node. Okay, finally we come up with sorry, that is also branch, and finally we come up with the result, right? That is what leaf. It is an apple, it is a banana. Okay, now you guys are understanding basket is a root node, and the remaining thing like based on the shape, circle not circle, and then we are having color yellow and red. So that is what the internal node. Finally we come up with the answer, right? It is an apple, it is a banana. Okay, so it is an apple or it is a banana. So that is what the leaf node. Okay, so guys, this is what the overall understanding of this decision tree, guys. So hope you guys have clear understanding, because like we are going in a breathwise manner. Once we go for a coding and then we have something like we go in a depthwise. Okay, hope you guys have a theoretical understanding of it. Okay, yes sir, over to you.
Yeah. So decision trees are, guys, they are non-pragmatic, okay? Non-parametric, okay? Models that uh, partition data based on the features. Like, so we have different features, so they partition on a, they are so there is no uh, specific parameter, non-parametric, okay, models are there. So we create a tree-like structure. Okay, we'll have a root node, we'll have internal nodes, we have leaf nodes. But trees, or as I have already mentioned, there are different kind of decision trees, guys, huh? So um, we have different kind of decision trees. We use for different algorithms. Okay, so they are like tree like structures. Tree like, you have root, suppose root that is in the soil, so it is from the root. Then you have stem for a tree, then you have leaves, so branches and leaves. So similarly, the scientists have just observed the trees and they have designed this decision trees based on that. So in the root node, what is their starting point of tree? Like the same way, the when you see tree, that is the starting point, that represents the entire data set. Okay, decision decision trees, like that represents the from the root node, it represents the entire data set. And then we have internal nodes. Internal nodes are nodes that split the data based on feature value. So we'll have different classifications, okay? And then those classifications will be subdivided into leaf nodes, okay? Like branches, huh? From the stem, then you have branches, right? And then you have each branch will have a sub branch and then leaves. So similarly, we have the third point is leaf nodes. We have uh, simplified here. We have not gone into sub branches and branches here, but you can imagine a tree and then you can remember what are decision trees, so that the inspiration is from the trees only, okay? The natural structure of trees. So leaf nodes have terminal nodes representing the predicted class for a particular data point, okay? So this is how a tree is defined. Decision trees are defined in AI/ML data science. So these are very important things you need to remember to reinforce learning. Go watch all the session 5 to 10 times so that you'll absorb this information and you get familiar, build your consciousness around it, awareness, so that you know what are decision trees, what are regression, logistic regression, what are different methods, what are those algorithms, so that where we use them, what is the purpose, what are the limitations, what are the characteristics, on which data we use them. So these are the very, very important things you need to remember and absorb. Let's move to the other slide.
Yeah, sure, sir. So next, let's see what's model we are having. Random forest, guys. So I think that this is a very interesting model which I love the most because like let's see why here it is. So random forest is an ensemble learning method that combines multiple decision trees to provide prediction accuracy. They reduce the overfitting and enhance the generalization. So the thing, what is random forest? Okay, multiple decision trees makes a random forest. That's it. Okay, consider we are having a basket, okay, basket of fruits, okay, and we are having a fruit called as apple, okay, we are taking apple and we are having different trees, decision trees, okay. First decision tree says it's an apple, second decision tree it says it's an apple, third decision tree says it's a banana, okay. Based on the majority voting, the final result will be apple, right? Because two decision trees says it's an apple and one only says banana. So based on the majority voting, it says apple. So now the overfitting problem is reduced and it is also generalized. This is called as random forest. Okay, multiple decision trees blend together in order to make the decision. Then it is called as a random forest. So it's an ensemble technique because it consider or it's multiplies or combines the multiple models to improve the performance. Next is bagging. Okay, randomly sample data and features to create diverse trees. Okay, because like we will be having all the data and we will be playing with the entire data so that the model will be generalized. Finally, majority vote predicts the class based on the majority votes of the trees. Okay, instead of going for a single thing, majority voting, it is for a classification. Okay, but for regression, it will be like a average value. But let's focus on it. It's a majority voting for the classification. So this is how the decision tree works, guys. So major thing is collection of decision trees makes the random forest. Okay, so this is how the random forest works. So that's it, guys. Okay, yeah, sir. Over to you.
Yeah. So see, random forests are like they as we have represented like forest kind of thing, but they are multiple decision trees actually. We have combined the scientists. They have combined multiple decision trees to improve the prediction and accuracy. Prediction accuracy. So they have just combined multiple decision trees. You just need to remember. Random forest is equal to multiple decision trees for improving prediction accuracy. That's the simplest way to remember. And they reduce overfitting, enhance generalization. So overfitting is reduced because of that, because uh, we have multiple decision trees and obviously when we have multiple decision trees, that means we'll have multiple features and data points also, right? Data sets also. So that reduces overfitting. Okay, so random forests are ensemble learning. Ensemble learning methods is combining multiple decision tree, multiple ways, to improve and predict the accuracy. That's why you will learn ensemble learning in future. So this is we ensemble different types of decision trees so that we can improve the prediction accuracy. So then we have ensemble learning, which combines multiple models to improve performance. Simple. So ensemble means it combines different models, okay, to improve the performance. That is the objective. That's it. You need to remember that way. Then bagging randomly samples data features, create diverse trees. So bagging is we randomly sample data, okay, through bagging, and features to create diverse trees, so that we'll have different uh, insights, right? And then we reach a conclusion, right? So that's why we use bagging. You can see sign also. It is randomly, it picks up the data and the features to create diverse trees. Okay. And then we have majority vote, predicts the class based on majority vote of the trees. So it also has, random forest also has limitations, guys. So it is, no algorithm is perfect. You'll see merits and demerits of each and every algorithm, whatever you're going to be familiarized. So we just need to know the limitation. What is the limit of this particular algorithm? What is the limitation? What I can do? And we are always probabilistic. We are never that any algorithm is 100% perfect. Okay, so have that attitude toward the algorithms. Okay, let's move to the other slide.
Yeah, sure, sir. Okay, next is support vector machine. Okay, so it is a different thing. Let's see. Support vector machine or a supervised model that find the optimal hyperplane to separate the data points into different classes. They are known for their robustness and ability to handle high dimensional data. I will put it in a simple manner, guys. Let us consider we are having a like a ocean, okay, or a sea, okay. So there will be a point, okay, there will be a straight line that separates the sea and the land. That is what the hyperplane do. The line, right, that separates the sea and the land, that is what the hyperplane, think of in this manner, okay. So this is what the support vector machine, it has a line or a hyperplane that separates the two different classes, okay. It can be multiple, I'm just saying in a manner that it can be two different classes, that is binary classification, or also it supports a multiple classification. So what is the strength? It robust to outliers and high dimensional data. It can handle a large volume of data, separation of large volume in different dimensions. Whereas for limitations, uh, this has a limitation, like can be computationally expensive for a larger data set, because like since it can handle a large volume of data, whenever you train the model, it's going to take more time. It's because it's going to train all the large long volume of data, like a huge volume of data. So that's the reason it's going to take more time. So it is a strength and it is also a weakness, okay. So that is what all about the support vector machine. Yes, sir, over to you.
Yeah. So SVMs are, guys, they are very powerful. Okay, I'll say in supervised learning models. So they find the optimal hyperplane to separate data points into different classes. That is the beauty of SVMs, okay, support vector machines. So they are known for their robustness, ability to handle high dimensional data, because you can see in the image there are hyperplanes. Hyperplanes means multiple, the multiple planes. You can see there so there are different kind of planes. So because there are multiple dimensions of data, you can see it's like mountain like range. Yeah, so there is different kind of data. You will see there is a ups and downs and different dimensions. And that is why for that SVMs are very, very robust. They are very useful for ability to, they will handle high dimensional data. So they are used for that. So whenever you have such kind of data, so you can use, you may use SVMs. So strength is robustness to outliers and high dimensional data. So they are very good for outliers, huh? Robust to outliers, okay, and high dimensional data. And limitations can be computationally expensive or large data. Suppose you need to have compute is a big thing for data, guys. That's the, I'll say, the biggest thing. If you can also become a world's best company in today's times if you have a compute power, because there millions billions of dollars are spent on compute power. So with SVMs, the limitation is compute power, so it is expensive for large. Until unless we have quantum computers in future, so then it will be lesser. Like if you see 50 years back, even 1 GB was so expensive. Even you can't think of 1 GB. So same
Yeah,
way,
it's real so
uh,
because like we need a quantum computer, right?
yeah, we need a
So to
quantum
do that
computer.
much processing,
Yeah,
right?
processing or
So
hmm.
yeah, guys, like yeah, as sir is explaining, like this uh, the thing that we require for a yeah, guys, like we are explaining like the quantum computing, right? So whenever we read we gonna work on this kind of models, we definitely gonna require high computation. Yes sir, you just continue. We are just talking about some
Yeah, so
context.
these are the limitations, guys. Strength is robust to the outliers and high dimensional data, but limitation can be computationally expensive for large data set. So that is the, but it is computational problem, not SVM problem, guys. So if we have high computer, we can use SVMs for quantum computers and supercomputers, and then we there is no limiter what they can do SVMs. They are very powerful. So let's move to the other slide.
Yeah, sure sir. Yeah, guys. So we have come up to the end of this classification model. So what is the conclusion and the key takeaways? Classification algorithms are essential tools for supervised learning, providing insights into a data patterns and enabling accurate prediction. Understanding different algorithms, their strength and limitation, and appropriate evaluation metrics is crucial for successful model development. Okay, guys. One thing you can see we're gonna see lots of model in different categories because machine learning is divided into different categories like supervised, unsupervised, and reinforcement. Inside supervised, we have a category classification and regression. Inside that regression, we're gonna see multiple models, linear regression, and then multilinear regression, like that we're gonna see, and then ridge regression, like loss of regression, like those things, L1, L2 regression. Whereas in classification, now we have seen nearly 5+ models, right? Support vector mission, and then decision tree, random forest, logistic regression, and there are n number of models, guys. So for your data set, for your application, based on the computation that you are having and accuracy, you need to fix what model is going to be useful for you. Okay, that's a major thing, guys. You guys need to decide what going to be your selection of model for the particular data set. Okay, so that's going to be a key takeaway. So yeah, that's from my side, sir. Yeah, so over to you.
Yeah, the conclusion is, guys, as Raja has already explained very well, he has explained. Okay, so uh, the classification algorithms are essential tools for supervised learning. Right now, let's focus here. Okay, in this moment. Okay, so providing insights into data patterns, enabling accurate predictions, understanding different algorithms, their strengths and limitations, appropriate evaluation of metrics, crucial for successful model development. So they are very like classification algorithms. So you know, uh, So you should know what is classification algorithm, what are they used for, what is the purpose, what is the objective, what is the limit, what is the so there are n number of algorithms, sub algorithms in regression. There are different logistic regression, and in there are other also, like we have seen random. In trees there are different decision trees. You will see random forest. If you have multiple, you do um, ensemble learning, whatever. You have different kind of algorithms and sub algorithms. Just learn few algorithms first and know the definition conceptually very clearly, that what is, don't make it complex, be very simple. Like suppose you want to know what is this classification algorithm used for, so it is for use for classification problem. Okay. Logistic regression, it is used for categorical, like, problem. So this is how you need. And whenever you have data which is problem with categorical, this, so you know that which algorithm you will use. Similarly, if you have a classification problem, you know that which algorithm I'll use for classification. So this is how you relate it. Remember, absorb, digest, and apply. So see you in the next session. So go and watch all the sessions 5 to 10 times. Write in the comment section. Give us feedback so that we can improve continuously. And subscribe to our channels, and press the bell icon so that you get notification for each session is which will be available. And stay focused, consistent. Consistency is the key, guys, for success. Continuously learn, do reinforced learning 5 to 10 times. Watch all the session previous so that you will build muscle memory and long-term memory. Thank you so much. See you in the other session.
Bye, guys. See you all in the next session. Bye.